Hello, welcome to the SC4X live event. We're very excited to have you. Our guest today is Dr. Daniel Merchan, and we're going to talk about applications of machine learning in supply chain management. Before I introduce our honored guests, I just want to give you a couple of sort of house cleaning notes for the course. So I'm your course lead, Dave Carell. You've gotten many emails from me, and you've got one last night reminding you that for verified students, your week 7 graded assignment is proctored. The whole thing is proctored, and that can be sort of a tricky thing to do on your end as the learner. So we really encourage you to take the practice proctored exam, to read those many pages of detailed instructions, and to make sure that you can execute the exam in the proctored settings. We're doing this because this is the last course in the sequence for you. And if you're going on to take the CFX, that will also be a proctored experience. So what we're hoping for is you can try it now, get used to it. It's honestly frustrating, so we understand that for you. So please try it now when the consequences are perhaps not as high, and then you can understand it before you go through the experience with the CFX. I hope the midterm went well for all of you. I've been watching the scores as they come in, and it has been going really well. So I'm really happy for you guys. Okay, the main event. We're very honored to have Dr. Daniel Merchan here with us. Daniel recently completed his PhD working here at MIT with the Megacity Logistics Lab. He has quite a bit of experience, particularly as it relates to big data and working with companies to solve logistical problems. So it's really an honor to have you here, Daniel. Thank you so much.
Happy to be here. Thank you for having me.
I wonder if, to start, could you tell the viewers a little bit about your experience in this world of supply chain and big data and some of the projects that you worked on?
Sure. So as David said, I recently finished my PhD here at the Center for Transportation and Logistics, working on how basically we can help companies use data and use analytics to innovate last mile delivery operation. That has been the space in which I have focused. E-commerce is pretty exciting at this point, and also in general, last mile operations in large metropolitan areas offer many opportunities for innovation. So my research has focused on how can we bring these new sources of data that we now have available, how can we bring classical methods that we have been using always in logistics, like optimization models, along with machine learning methods to come up with better decisions for logistics operations.
Excellent.
And for that, personally, I've worked with companies in Latin America, India, in the United States, and even though the context might differ, but also there are some challenges that are quite similar across these geographies. And I think that both data and these new machine learning models can offer an opportunity to tackle some of those problems.
Great. When you work with these companies, are they all part of your own dissertation project, or is this across a variety of projects?
It's generally across a variety of projects. Of course, as a PhD student, you want to align as much as you can your research with the work you do with the companies as part of the research project CTL engages with. But it doesn't have to be the case. So nevertheless, even though a project might not be part of your dissertation, you still use some of the insights you learn from that project. You still may use some of the data you got for that project to strengthen your work. And that was my case. My primary case study within my dissertation was the operation of a large e-commerce platform in Latin America, in Brazil specifically. They were interested in redesigning the last mile operation in the city of Sao Paulo. It's a very large, they serve around 15,000 customers on a daily basis. So they had a complex network, and they needed to run, they wanted to redesign their operations to support future growth and to make sure that their operations were as efficient as possible. However, I was exposed to very similar problems with other companies in other cities, and that's where I got the opportunity to validate some of my ideas from my work in these other projects. So it's a bit of both, I guess. You have case studies that are a big portion of your dissertation, but at the same time, you have other projects, you're exposed to other cases that help you strengthen your ideas and test your methods.
Excellent. But before we start on your dissertation, many of our learners have undergraduate or maybe master's degrees, or they're
Yes.
thinking about master's degrees, some even thinking about PhDs. Could you tell the learners just a little bit about your undergraduate and graduate education before your doctoral degree?
Yeah, absolutely. So I'm originally from Ecuador, the southern part of Ecuador. My town is called Cuenca. Grew up in Quito, got my undergrad at my home university in Ecuador, Universidad San Francisco, in industrial engineering.
Okay.
And that's how I had my first exposure to the logistics world through one of my undergrad classes. Then came to the United States. I did my first master's at Texas A&M University, a master's in industrial engineering. Then went back to Ecuador, worked primarily in an academic environment. So I was basically teaching undergraduate courses in logistics. And that's how I became interested in pursuing a PhD. I was very involved, let's say, in the academic world. Was teaching a lot, but not doing so much research. So I wanted to develop that profile. And when I was in Ecuador, I learned about the Scale Network. MIT was CTL and MIT were launching the Scale Network, and they were beginning their efforts in Latin America. So I said, well, this is a perfect opportunity. I really wanted a PhD that looked both at what happens in the developed markets, but also in emerging markets, because they all offer very interesting logistics problems. And it took some time to prepare, of course, to come to MIT. But after a couple of years of preparing exams, GREs, TOEFLs, and strengthening my profile, I joined MIT in 2013, first as a master's student, and now I recently completed my PhD.
Well, we're very glad to have you.
Thank you so much.
Maybe now would be a good time to tell the learners a little bit about your dissertation project.
Sure. So as I was saying before, this case study was in Brazil. And what this company, the challenge this company had, they had already a multi-tier distribution network. Basically, when we say multi-tier, and maybe you have seen this already in previous classes or in previous live events. I think Matthias was here a few weeks ago. Basically, when we refer to multi-tier distribution, we mean this urban distribution networks that combine large facilities, large fulfillment nodes with smaller satellite facilities spread throughout the city to facilitate transshipment or as a temporary storage locations. So the company was basically interested in understanding to which extent their current network was efficient and also plan for future growth. So we engaged in a project in which we helped them basically redesign their operations. And this redesign entailed understanding whether the current location of the facilities was the optimal one, and they should look into other possibilities. Understand also the allocation of different service areas, different neighborhoods within the city to those facilities, and finally the vehicle choice they had to make. Whether in downtown Sao Paulo they should use the same vehicle as probably they use in a residential neighborhood. So that was kind of like the decisions they were facing. So this is a classic optimization problem. So this is where you basically bring your location models or your location routing models and try to solve this problem. However, as we were testing classical methods that we've used in logistics, we'd notice, and if we talk about optimization, usually you're trying to minimize the cost or maximize some sort of performance measurement. And what we noticed is that there was an opportunity to improve our cost predictions to then better inform the optimization model. So in this setting, for instance, part of what we want to optimize is the cost to serve a neighborhood. And that cost to serve a neighborhood is a function of the distance or the time it takes you to actually operate in that neighborhood. And that might be driven by the local traffic conditions, the road network you have available. So it's quite a complex scenario. And what we notice is that classical methods were failing to provide a good prediction on how much it would cost to serve those different neighborhoods. So that's where we brought machine learning methods to help us improve our prediction of the time it would take to serve the area, the distance would be required to serve the area, and ultimately the cost estimates of serving that region. And with those better estimates, now we go back to the optimization models and we basically redesign the network, or we run our analysis to understand what is the optimal network design. So I think this is an example of how I think machine learning can have a role in decisions in supply chain management, is by actually providing us better ways to predict either demand or cost or distances that we then use as inputs to the other decision support systems, such as simulation models or optimization models, that ultimately help us make better decisions.
Could you tell the learners a little more about the predictions?
Sure.
The models, how you were getting the predictions? Were they set neighborhoods, or how was it determined, the category for the prediction? Does that make sense?
Yes. So those of you that have taken SC1X maybe remember Chris's lecture on routing approximations, right? So they use a very simple analytical expression to calibrate, to try to approximate how much time, well, the distance that you will need, or the expected distance you will need to serve a given area. What we notice is that those approximations might work well in some settings, but especially in cities where you have these levels of complexity because of traffic, because of the road network properties, one-way streets, obstacles, and so on and so forth. Those approximations were underperforming. However, through new sources of data, Google Maps, for instance, or OpenStreetMap. So basically, by bringing new layers of information to these classic models, we can significantly improve the prediction. So, I mean, technically, this is a supervised learning problem, because we will use routes to train the algorithms. We will use routes or near optimum routes with their corresponding distance estimates to train the algorithm. But the key part of that prediction was that we were able to bring new sources of data that were probably not being used before because they were not available. Now it's, for instance, very easy to extract real distance estimates or time travel estimates from Google Maps. This was hard to do 5 years ago. Now it's becoming easier. So I think the key part of improving that prediction in any neighborhood was that we could use data that was specific from that area or from that region within the city to actually calibrate the predictive, to tailor the predictive performance of the algorithm to the local conditions of that area.
Excellent. Could you tell the learners a little about the data collection and perhaps the data cleaning work that went into doing that kind of project?
So that's always the fun part, right? Data cleaning, data processing is always fun because it takes quite some effort in the sense that depending on the data source you have available, you might need to spend a little time or a lot of time cleaning it. I think we use in that particular project 3 sources of information. One was company data. And usually company data is well formatted, well structured, and that was relatively easy to process. And we use company data to predict, to approximate or predict the demand in a neighborhood. So we use past orders to predict how much or what would be the intensity of demand in a given zone. But then to bring road network data and traffic information, we use Google Maps. The Google API is quite easy to use now, and it offers high quality data. So there's very little cleaning involved. However, if you want to bring road network information, like basically how many one-way streets you have in your neighborhood or stuff like that, OpenStreetMap is a great data source. However, it's crowdsourced, so it's not always fully accurate. So there might be some data cleaning that has to take place. I think generally these data sources that we need are becoming more reliable and more accessible, but still the data cleaning process is important. And I think the key aspect of the work we did in Sao Paulo was that we were able to triangulate not just company data, not just transactions and orders and even GPS traces from the company, but we also brought information from the context, from the city, the traffic, the road network. And the combination of those two is what I think really drives an improvement on the prediction models we developed.
Excellent. I see we already have a question from a live viewer. And just to remind any of you that are watching now, you can participate in this discussion through Slido. So you have that link in the message from me and on the course page. So please let us know if you have any questions or ideas. So Jesus Madrid asks Daniel, to what extent and how was simulation used in this research?
Great question, thanks. So I was mentioning before that we managed to combine basically machine learning with optimization models. But you can think of it exactly the same way if you want to combine machine learning with simulation. At the end, Simulation is a tool then in which we try to replicate the system to understand how it performs. And you can still use machine learning to come up with better parameters, better estimates of the cost, of the time, or the distance that eventually feed your simulation model. So we have done some simulation analysis in last mile operations because sometimes our corporate partners are interested in finding an optimal network design, but sometimes they are interested in understanding how does their current network perform under different demand scenarios. And that's where we use simulation. So we simulate, let's say, the operations under normal demand patterns or the usual demand patterns, but then we simulate also when they have a peak season like Christmas or Black Friday. And actually and the logic is the same, right? So we use machine learning to improve our predictions, to improve our estimates and our parameters that eventually feed and inform either the optimization or simulation models. It really depends on what you want to do. It really depends on whether you're more interested in understanding the performance of your system, or you're interested in a network, in coming up with an optimal or near optimal network design. Usually in practice, companies do both. And you can leverage the same tools and the same data to achieve both goals.
Excellent. Thank you for the question. Thank you for the answer.
No, my pleasure.
You mentioned when you were talking about this project that you used machine learning techniques to come up with better predictions. Do you have a sense by how much the machine learning predictions outperformed the classical predictions that did not include these new data sources?
Yes. So it really varies based on certain conditions, but on average, we found that by using these improved models, we were able to bring the error down by approximately 20–25%. So the improved prediction still has a error level of between 10 and 15%, depending on again those conditions, but it's about 25% better than what we were doing before. So it's a significant gain, and I think the key part is not so much the algorithm itself. Is at least in my example. In other cases, the algorithm might be playing a significant role in that improvement. I think in this particular case was that we were able to use better data, and I think those two pieces are very important when we do machine learning studies and machine learning projects. It's not just about the availability of no algorithms, because you might be using maybe a classical linear regression or a classical logistics regression, but just by using better data, you can improve your prediction. So it really depends on the specific case.
Just out of curiosity, could you tell us about the prediction model, what models you used?
Sure. So we use a variety, but we actually always start, and that's something we do in every single project. We try to use a combination of models. So if we're predicting, let's say, travel distances or travel times, just to give an example, this is probably a supervised learning problem in which we can try regression analysis, but you can also try random forest. And it's hard to say whether one is better than the other before trying them. Right. So usually in practice, what you do is you bring a set of models and even different variations of the same model. You have a basic logistics linear regression, for instance, and then you can try a polynomial regression, or you can try a lasso regression. So different versions of a classic logistic regression problem and other models such as random forest. And what we usually do, at least in our team, we try all of them. And then we assess which one gives us better performance, but also which one gives us better insights, right? So it helps us understand the correlations and the relationships between the variables we're using to predict and ultimately the measurement that we are interested in predicting.
That's great. And could you speak a little bit about how you choose which model is better than others? So there's sort of classic measures of model performance, but it sounds like maybe there's some other things that you consider too. And I guess I asked because I know for our learners, for example, in your midterm exam, we asked you to look at area under the curve and then tell us what was best and move on, but maybe it's more detailed in a real project. How do you weigh those measures?
So the way we usually go by this is if you have several models you want to compare, you have to be, of course, the first thing you look at is the R-square as a measure of model accuracy, how good your model is. But you have to be careful because, especially if you have a large data set, there's always a risk of overfitting the model. So basically, you are modeling the noise and not so much the signal. So that's why it's usually a good idea to break down your data set into a training and a testing data. So you train your model with the proportion of your data set, and then you assess the performance of your model on a data set that has not been used for training. So that's a way to control for overfitting. And then you usually monitor the R-square both for the training and the testing data set, so that you make sure you don't overfit the data. Although there are other techniques to also help you not to overfit, but usually splitting your data in training and testing, it's the very first step. And I think R-square, if we're talking about predicting a numerical value, the R-square is usually the measurement you use to compare. If we're predicting a category, and usually the classification accuracy, but it's some measure of model accuracy is what usually you use to compare different models against each other.
Excellent. Thank you. You know, we've been asking so many specific questions. I know you brought some slides to share with our learners. Would this be a good time to take a look?
Absolutely. So I brought a couple of slides so that we can also talk about the different types of machine learning models that can be used. Because perhaps the most intuitive one is we can say, well, I want to predict demand. Actually, demand prediction is a critical decision supply chain managers have to do. And that's where there are some opportunities for machine learning, and we can discuss that in a minute. But we have the world of supervised machine learning, which is how we predict a number or a category based on data that we have observed. But there's also the world of unsupervised machine learning. And the easiest way to think about it is, what if we have a data set with multiple variables, but you don't have a classification, and you want to come up with a classification? And you can think of this as, I want to create a customer classification based on several parameters that I've never combined them before. And the more parameters you have, the more difficult that classification becomes. It's less intuitive. So in unsupervised learning, what we usually do is we build machine learning algorithms to help us understand the structure of the data and ultimately derive classifications. And I have an example in the screen. This is part of the research we have done with my colleagues at the Megacity Logistics Lab. Imagine that you are an urban logistics planner, or you are a supply chain planner in a company, and you're trying to understand a city. And this is actually a screenshot from Quito, the capital of Ecuador. That's where my home is now. But the idea is that, so from a logistics standpoint, you might want to classify the city, and maybe the classification that you get from the city itself, the neighborhoods, is not as important to you because it doesn't include the variables that are relevant for logistics. So in this project, we actually used k-means clustering, one of the unsupervised machine learning methods, to help us group the different areas of the city. Each one of those dots you see in the map is a square kilometer, and that's how we segment the city. And we want to try to understand which of those square kilometers are similar, have similar characteristics, and then we can group them together, we can cluster them together, and which of those are unique. And to give you a sense of the ones in purple, those segments share the several variables. Specifically, these are where the manufacturing district of the city is concentrated. So by bringing data from basically census data or data from economic activity, plus other variables such as the road network data, such as where my customers are. So we're basically bringing to this analysis different layers of data, different variables that we think are relevant for logistics. This is, of course, one example. But in this analysis, we thought, well, what are the variables that drive last mile operations that make it more difficult and more complex? And that's, of course, population density, the density of the retail establishment, the retail dynamics of the sector, but also the availability and the type of road network you have in there. And but of course, these are completely different worlds. Population density, road network information. It was not intuitive for us to see how then we classify these together. So we used machine learning for that, and actually came up with this nice classification of the city into stereotypical zones that we can then tailor logistics decisions to those areas. So we can then tailor either policies or logistics strategies to each one of those segments in Quito. And for instance, you see some of those clusters are larger. Maybe those are the residential areas, whereas, for instance, the blue cluster that kind of spreads through the city, and those are different residential areas that are both in the northern and the southern part of the city, whereas you have a few segments that are, a few clusters that are just made out of 3 segments, very small ones. And those that means that those are very unique zones. And actually that happens to be downtown Quito and also the entertainment district. So those zones have very unique characteristics. That is actually where most of the density of demand for, let's say, restaurants or retail establishment concentrates. So by using clustering analysis, we now are able to segment any city in the world based on these variables and then start tailoring our decisions, either from private sector in terms of tailoring strategies or from the public sector in terms of tailoring policy measurements, basically.
This is a great example. Thank you so much. And you said that you spent some time growing up in the city?
Yes.
So when you looked at this map, do the colors correspond to your understanding of the city?
Absolutely. Yes, absolutely. So, and that's a great point, because and we can use machine learning, but that doesn't replace human judgment, right? And it's always important, once you run the algorithms, to validate and to double check and actually make sure that the result that you observe are consistent what would you expect. At least I would have expected downtown Quito to be unique, and that's what we see. However, it was also harder to think of what are the other categories that we will find. So that's a combination of judgment, of subject matter expertise, local knowledge, along with the use of machine learning methods to actually come up with this classification. And this is one example. Another common example of, maybe not in the logistics world, but another common example of unsupervised machine learning is basically what you guys are doing now. We're on YouTube, and YouTube use these recommendation systems. So does Amazon when we want to buy something online, Spotify. All these web platforms that now give you recommendations of things you might like, they're using unsupervised machine learning to say, well, Dave, based on your search profile and the things you've been watching, you might like this new video or this new book, right? Yeah. So this is another example, more probably, that we're a bit more familiar with. And actually, the truth is that we are using machine learning every day in different apps and different tools that we use as part of our daily lives.
Absolutely, and I think that's a great example. We talked a little bit about in lecture of the finding common products, or that might be interesting to a consumer. And I think it ties to this in that if I look at what's recommended to me, it might not be the same answer that I would give if you were to say, hey, Dave, what books do you read? I might give books that make me sound smart.
Yeah.
But the algorithm would know, no, Dave,
yeah.
This is what we've seen. And so we get maybe a surprising but sometimes truer picture of what the data really suggests. And I wonder, did you see anything like that in this city where maybe you would think, gosh, I thought this was going to be its own residential area, but perhaps it's a little more like something else? Do you find those kind of counterintuitive discoveries that are supported by data through this technique?
Yes, one example was actually the manufacturing district. So if we look at the city, and based on our expectation and our local knowledge, we really thought that we will see a similar manufacturing cluster in the southern part of the city. But even though there are some manufacturing facilities there, it's not as concentrated as it is in the north. And actually, the classification suggested that that felt really more like a residential with some commercial manufacturing activity, but the predominant, let's say, dynamic in that zone was, or the predominant land use, sorry, was residential purposes. So yes, we found things that we weren't expecting, but at the same time, we also confirm some results that were based on our intuition and our understanding of the city.
One more question on this. Could you maybe walk the viewers through, and this could be just hypothetical, now that you've found these different groups and you're doing it for the purposes of logistical decisions, what kind of logistical decisions would be different for servicing, say, the yellow dots compared to the purple dots?
Right. So actually, this is a project we finished recently in collaboration with a large development agency and local governments in cities in Quito, Bogota, and Lima. And our idea was, based on these profiles, how can we inform policymaking? And one example is that if we look, for instance, at the two clusters, the two most relevant clusters, downtown Quito in brown, and the other one, the entertainment district in red, the smallest ones. These are both dense zones, very important from a logistics standpoint. They have a very large retail density, but stores in downtown usually operate from 8 a.m. to 5 p.m., regular business hours. Whereas in the entertainment district, the restaurants operate maybe from lunch to midnight. So once you capture those differences, then you can tailor policy, because part of urban freight policy generally entails restricting access within certain periods of time. So this type of analysis can help them understand, well, maybe this, given based on this profile, then it probably doesn't make sense to establish a access restriction, let's say around noon in the entertainment district, because that's where most of the activity is taking place. So this can actually inform the characteristics of both retail dynamics, logistics operations in the zones, and then, for instance, help us better understand, better tailor access restrictions, or even the development of infrastructure. Parking is usually very limited, and by understanding these patterns, we can not necessarily dedicate parking full time to freight operations, but we can say, well, within this time window, these spaces that are usually used by residents now can be used by trucks, just within these 2-3 time windows, so that we can facilitate logistics operations in these areas.
Oh, that's great. Thank you.
I think there's another question.
Oh, there is, and we have a great one. Just a reminder for those of you watching, you can interact with Daniel and myself through Slido, and it looks like we have a question. Great. This is from Han. He says, congratulations on earning your PhD. And he points out rightly that we used Orange for machine learning. Could you talk about what you use as a software package?
Yeah. So Orange is a great tool. I like it a lot because it kind of has the applications ready to use. However, sometimes when you're dealing with new problems and with large data, you might want to have some more modeling flexibility. So in my case, I use Python as my main coding environment. And Python has a set of great machine learning libraries, specifically sklearn. It has all the supervised and unsupervised machine learning models already implemented, kind of ready to use. So Python is a very important part of our research. And the good thing about Python is that it's not just machine learning specific. Actually, Python is a general coding environment, and it allows us to combine in the same code machine learning models with optimization models, with simulation models, something that it's, for instance, difficult to do if you're using Orange, because you cannot really embed an optimization model within the Orange platform. So that is the tool we use, and I think an important part of it is that it's open source. So Python is open source, so that's why we like it. We don't have to pay for it. And in general, the data science community is advocating more and more for the use of tools like Python or R, these free open source environments for machine learning. So there's that is usually the tool set we have. And of course, on top of that, sometimes we use Tableau to visualize results. Tableau is a great tool. It's not free. It's not open source. I think Python is getting better at visualizing things. So as Python gets better, we'll probably transition even our visualizations to Python.
It's a great answer, and thank you for that great question. And to follow up, I'm going to skip ahead on some of the questions, but one of the things I wanted to make sure I asked Daniel on behalf of the learners who are watching is, I think many of our students will be inspired by the work that you do and the project that you've done. What are sort of the skill sets that you think learners should develop now to be able to perhaps go into a graduate program or even a consulting position and do projects like the ones that you're sharing with us?
Right. So I'll answer that question in two parts. I think one is what learners can do, and the other is what organizations should be doing or can do. I think learners, the best thing they can do is they continue doing what they are doing now, leveraging the resources they have now available, tools such as edX, Coursera, to take machine learning courses and AI related. And this is actually a very large variety of options out there, all the way from the course that teach you the implementation aspect of it. It's just, if you just want to learn how to implement a model in Python and code it and run it, there are courses for that. There are courses for, if you want to learn more of the math behind the models, like the frameworks, the analytical frameworks, and a bit of more of a theoretical understanding of the problems. You also have courses for that. Actually, there's one very popular course in Coursera by Stanford on deep learning that it's out there. Anyone can take it. So I think that's one way to go. Actually, I have myself throughout my PhD leveraged some of the Python courses available on edX to learn those skills that I couldn't find in a regular class. So I think that is an important piece, and especially supply chain managers. I think they need to become more and more confident, comfortable, and familiar with analytics. And I think SC4X is part of that vision. And the reason is that if we want to, and that's where I get to the second part of my answers, if we think this from an organizational perspective and how companies can leverage this potential, it's really not so much about the tools. The tools are secondary. It's about the teams you put together. It's about the people you put together to work on these problems. And based on subject matter experts suggest that you usually need to have, and we have witnessed this in practice, that you usually need to have a combination of 3 skills for tackling these problems and for basically leveraging the potential of data analytics in organizations. First one is analytics. Basically, you need people that understand deep learning, that understand neural networks, that understand all this, basically the math behind these models, because they are actually the ones basically building this analysis. You need computer scientists. That's the other set of skills you need to have. And because they are the ones processing the data, cleaning the data, and implementing and scaling the models that the data scientists develop. And the third, I think the third role that you need in those teams, and they need to work together, of course, is actually the subject matter experts. In this case, the supply chain managers, the logisticians. And that's how we actually make sure, by having those 3 roles in a group, and if you rarely have all that in one person, you always need teams. You always need teams because people have skills, and when you combine those is where you get the most of the value out of it. And I think that especially for supply chain managers, they are the bridge between what the analytics and the computer science do, and then the decision makers within the organization. Some people have used the term data translators. But it's just the idea that I am someone that is very familiar with the business. I know the business, I know logistics, I know the operational aspects, but I'm also familiar with the analytics, and I can translate what the analytics team is doing to what the organization needs to decide upon. And so that role is very important. I think that role has to be taken over by the subject matter expert, by the logistics people. However, they need to be comfortable with analytical models. Maybe they are not the ones that are going to be building a deep learning algorithm, but they should understand it, and they should be familiar enough so that they can extract the value out of it and connect that to the needs of the organization.
That's excellent. Thank you so much. And as Daniel said, I think our course can hopefully be a part of that for our learners. Those of you that want to go deeper into Python, into coding these things yourselves, Daniel just gave a lot of great resources there. And hopefully on our side, we can get everyone comfortable with some of these tools so that you can be the translator that Daniel talked about. It was just meeting with a partner of ours recently who said that same story. You know, we have all of this data, we're getting all this great analysis, but we need people who can translate it to the pictures and the problems that our company faces.
Yes, absolutely. And I think usually translating data means telling a story, right? Translating complex analysis into decisions, actionable decisions, is usually entails telling a story about the data and then translating the data or those results into something managers can use to make a decision. And I think I just wanted to add that visualization is an important part of that puzzle, because the visualization, I think, is the way how we can convey complex analysis and complex models. How can we translate those into actionable and understandable decisions, especially for members of the organizations that are not as familiar with the analytics as the others are. And at CTL, we have been increasingly interested in understanding how to better visualize and communicate those complex analysis to decision makers. I think that's a part that shouldn't be underestimated. Communication, visualization, storytelling, it's a very, very important piece of the data translator role.
That's a great point, and it's an art in itself. You know, sometimes you see something visual that is beautiful, but I can't understand it.
Right.
Very complicated. I know there's power there, but I don't understand it. And sometimes you see something like what you prepared with your map here that I think is a perfect representation of some pretty complex ideas. It looks like we have another question. This is from Edmar, who asks about using econometric tools combined with machine learning tools.
Yes, we have. And actually, some of the tools are very similar, right? So you can use regression analysis from a machine learning angle, which is when you're more interested in predicting rather than understanding relationship, which is, at least as far as I understand, one of the motivations behind using econometric tools. So I've used econometric modeling in my own research to basically understand the correlations, for instance, between road network efficiency and the properties of the road network, the amount of one-way streets you have available, for instance, in the area. However, in machine learning, we're a bit more interested in being more accurate in our predictions. And that comes usually at the expense of interpretability, whereas where econometric models are basically strong at. So what at least the way we approach is, because also understanding this relationship is important, even though your interest is mostly about better predicting demand and trying to be as accurate as you can. It's always useful to have a better understanding of the relationship. So we usually start with a simple model, a simple regression to try to understand the correlations. And then building on that result, we get into the more advanced machine learning models that probably are less interpretable, but are better at predicting more complex relationships. So we use a combination of both, and I think that's usually a good idea, so that you have both, you kind of cover both ends.
Great question, Edmar. Thank you, and great answer. And I think it speaks to, we're in a really neat place as people who are interested in this topic, in that there's so much free software out there, and people can learn so much about Python coding to bring those models together in a way that would have been difficult years ago when you had sort of paid for packages that didn't necessarily have all of that capability.
Yep, absolutely.
This might be a nice time to look at our word cloud. So we asked you viewers to tell us which parts of supply chain management do you think could benefit the most from machine learning applications? And so bigger words mean more people thought that. So I might ask our resident expert to comment on some of these words and just say, maybe do you see this as supervised or unsupervised? Do you think about certain types of machine learning models when you think about some of these issues? What jumps out at you here?
Demand forecasting. I mean, I agree 100% with you guys on this. I remember when I came to MIT, first class with Professor Sheffy and Dr. Chris Kaplis, very first course, which is actually a replica of SC1X, very first course on logistics. Week 1, demand forecasting. So the demand forecasting is, a fundamental problem in supply chain management. And actually, I think that's where machine learning can play a role. We have used some methods, some classic methods, exponential smoothing. We have used even regression analysis to predict demand. I think the opportunity now is because we have more data and we have slightly better algorithms, or we have made improvements of the algorithm. And because we also have computing power, more storage capabilities. That's where we can really build more advanced demand forecasting methods. And actually, there's a very nice example that came up in The Economist a few weeks ago. It's a German retailer is using deep learning, basically advanced neural networks, to better forecast demand. And the reason is that they found that because they were not basically being good at it, they were underestimating the demand, and sometimes that led to delayed shipping orders to customers, or they just meant that they would have, if you place an order and you have 5 different items, you will send 5 different shipments. And of course, as a customer, you just want to have 1 delivery. You don't want to have 5, or maybe 2, but not 5 for sure. So by using deep learning and by moving away from just maybe 1 or 2 variables used to predict, they are now using 200 variables in their deep learning framework, all the way from past sales to weather data, to web searches. And you cannot do that with a basic linear regression. So that's where you need deep learning. And but by using deep learning, they've also improved significantly their forecast accuracy. And if you can predict better your demand, then you can plan your capacity or pre-position your inventory. So many decisions that depend upon your ability to predict demand. So I personally believe that demand forecasting is an area where machine learning can play a big role in helping us better predict those parameters. And then on top of that, we will improve all the other decisions surrounding our ability to predict demand, which is a fundamental problem in logistics. But of course, demand forecasting is just, I don't think is the only one. Many other applications. I'm not sure how much time we have left, but we can talk this for a little while. I think there are several areas where machine learning can play a role.
Oh, absolutely. Looks like we have another question. I want to make sure we get to all the viewer questions we can. Chris asks, are there new dynamics in demand that make machine learning techniques more suitable than traditional techniques?
Yes and no. I'm not sure if these are dynamics in demand. It is true that maybe because of e-commerce, maybe customer expectations are becoming more diverse and therefore becomes harder to predict. I think that might be part of the argument. But I think that the other reason is that we just now have better tools. So we have more data, we have classic and new methods, and we have more computing resources to leverage all those data sets to make better predictions. So as basically the example that I gave from my thesis, the methods are still the classic one. We're just improving them with better data. So I think that even though there might be some changes in the dynamics of the demand patterns, I think the key part of why we're talking about now about machine learning and all these algorithms is because we have finally enough data to train them and to make them useful for predicting. And we have enough computing resources to actually efficiently leverage these tools.
I think we are getting close to the end. Let me ask you one more sort of philosophical question, because I know that's your favorite topic.
Of course.
Thinking about how do experienced managers interact with machine learning now? Is it sort of replacing our decisions, or is it informing them? So could you sort of describe the human-computer interaction on logistical decisions today, and then predict for our viewers how it will be different 50 years from now as the technology advances?
Right. So I think the first thing that I would like to start by saying is that I don't think there's going to be such a thing as general artificial intelligence, in which robots will take over the things we do. However, there's going to be definitely changes in the roles, the different roles people now have and will have in the future. And I think I believe that what managers are doing now and will continue to do is just use data to better inform the decisions, but and machine learning and all these new technologies to better inform the decision, not necessarily replacing their experience, their intuition, and their judgment. It's just bringing some more information and different angles at a given problem so that the decisions are more robust. So I think machine learning analytics are meant to complement, not replace human judgment. However, there will be some roles, and this is something that's already happening in warehousing. A couple of years ago, robots in warehouses were just basically, we'll train them, we'll program them to do specific tasks. Now we see more and more, but because of the combination of robotics and AI, we see more and more robots taking over some of the tasks that humans usually have been doing. But those tasks are usually the ones that are more physically taxing or the ones that are more tedious. And then humans are basically taking over the supervision of those robots, the maintenance of those robots, or the control of those robots. So I think that we will see more of a coexistence of humans and robots in the workplace. The role of humans will definitely change, and that's something both companies, but also the educational institutions, the education institutions need to think about. Well, if based on these trends, what are the new skills that people in logistics should have so that they are still part of the economy. And but I don't think there's going to be such a thing as fully replacing the workforce. It's just there would be some tasks that are more suitable for robots, and others, even for instance, things that require precision or things that require some level of improvisation, humans will still be much better at least for the foreseeable future. So it's more about finding what activities are better suited for robots and for automation, and what others are better suited for humans. But both will coexist. At least that's what I believe.
I 100% agree. And what you said had me thinking about your work that you've shown us, and thinking about how having that better information can actually help a human better innovate. Because if we understand something at a deeper level than we did before, the human might get a new idea, and who knows how that happens, but it's a human experience.
Exactly, yeah, absolutely.
Before we go, we have one more viewer who has a question that I want to make sure that we get to. It looks like this viewer is interested in the work that you've done on classifying cities by demand, and wonders how, particularly in the US city of Washington, DC, could they get information about demand in different areas? Do you have any advice?
Well, in our case, we had access to company data. So that was, let's say, help us come up with those estimates. If you don't have access to corporate information, probably the best thing to do, and we have done that in the past, and actually in some of the studies I discussed earlier, we use population as a proxy of demand. So it's not, there's some error there in that prediction, but usually population density, especially if you talk in retailing settings, population density is usually a good proxy of the demand. And in the United States, at least, there is the population information is usually available, and it's the good resolution. It's up to date. So I would recommend looking for some population density or census sources to cover that gap.
Great. Well, thank you so much, Daniel. We are so proud of you here and excited for your completion of your degree.
Thank you so much.
Thank you for spending some time with our learners today.
No, my pleasure.
Thank you. All right.
Bye, guys.
Bye-bye, guys.